So in this part of the lecture, we'll prove that the first order condition of the convexity is also a sufficient condition for any general convex function, that is a mapping from an n-dimensional real vector to a scalar. So let's assume that we have function f, which is a mapping from a real vector to a scalar, satisfies that f of y is greater than or equal to f of x plus gradient of f of x transpose times y minus x for all x and y that belong to the domain of the function, which is a convex set. So the domain of the function has to be convex. So now let's assume that there are points t and t prime such that x, t times x plus 1 minus t times y belongs to the domain of the function. Since the domain of the function is a convex set, we can always find a point, we can always find a scalar t, and t prime such that this also belongs to the domain of the function. Likewise, t prime x plus 1 minus t prime y also belongs to the domain of the function. So now we can use this property of the function. So what we get is f of tx plus 1 minus ty is greater than or equal to f of t prime x plus 1 minus t prime y. Since both of these points belong to the domain of the function f, so we can write that f of tx plus 1 minus ty is greater than or equal to f of t prime x plus 1 minus t prime y plus the gradient of the function f at t prime x plus 1 minus t prime y, times the difference of these 2 points, tx plus 1 minus ty, minus t prime x minus 1 minus t prime y. Which implies that f of t times x plus 1 minus t times y is greater than or equal to f of t prime x plus 1 minus t prime y plus the gradient of, I'll just write it as lambda for now, just to save the space, lambda times, so this is lambda just to save the space, lambda transpose times, we can simplify this term, so this would be tx plus y minus ty minus t prime x minus y plus t prime y. So here this y is cancelled out. So what we get as a result is f of tx plus 1 minus ty is greater than or equal to f of t prime x plus 1 minus t prime y plus lambda transpose times t times x minus y minus t prime times x minus y, which implies that f of tx plus 1 minus ty is greater than or equal to f of t prime x plus 1 minus t prime y plus, now we will plug in the definition of the lambda, plus the lambda is the gradient of the function f at point t prime x plus 1 minus t prime y times this term transpose times x minus y times t minus t prime. So now we can write this as our function g of t. So this is g of t is greater than or equal to, we can write this function as g of t prime plus this is g prime at the point t prime, this entire term if g of t is f of tx plus 1 minus ty, then g prime at point t prime would be this entire term, g prime t prime times t minus t prime, which means that the function g is convex, which we get from the 1D case. So now, and also we know that f is convex if and only if g is convex, and likewise if g of t is convex, then f is convex. So this proves that this is both a necessary and a sufficient condition for f to be convex. So we just assume that f satisfies this property and that the domain of the function f is convex, and we obtain that as a result that the function f, when restricted to a line that intersects its domain, this function is convex, which implies that the function f is also a convex function. So that completes the proof of the first order condition of convexity, both the necessary and the sufficient conditions.